Okay. Good evening, everyone. This is the FrontRange6Meter group, and we're going to get a update presentation tonight from Dr. Scott McIntosh, who's been a guest with us several times before, and he's the Deputy Director of NCAR here in the Denver area. And the subject is our favorite subject, Solar Cycle 25. So again, let me just mute everyone and then I'll get Scott going and we'll take it from there. Oh, okay. All right, Scott, I think you're on, and if you have a presentation to share.
Oh yeah, I should probably do that, huh?
Yeah.
There we go. Can everybody see that okay?
Yes, very good.
All right, complete with jazzy graphic. Yep. Barfing Rolling Stone sun there. I just got to move this, see if I can get my cursor up. I'm working a large format monitor, so it's a bit of a pain in the butt. All right, so there we go. All right, well, good evening, everyone. This is my third time with you guys, I think. I'm going to do a quick recap. Hopefully quick. It's about 10 slides of where we were last time. In the dark old days of the middle of 2020. And then once I'm done with that, I'm going to show you an update that I prepared yesterday that was causing a little bit of a stir in the Twitter space. You know, a little bit of a stir is like 5 people. So as you can imagine, you know, there's things are happening. There's clearly seeing increased propagation. One of the last slides I've got, we've actually got a forecast of the solar radial flux out to about 2032-ish based on what we've learned so far. So you can take that with a huge pinch of salt, maybe a bucket. And then hopefully we will have some time for Q&A at the end. So I'm going to go over my recap. Then I'm going to show you what the state of the game is with respect to our friend the sun. And then hopefully we'll have a Q&A. And if you feel really brave, screen grab that last slide, because that's the one with the F10.7 forecast. So that I believe is rather important. So anyway, hang on, let's go. All right, so I'm going to jump in my time machine. I'm going to turn my video off so that I preserve my own bandwidth here. If I can actually find my cursor, can't do it. So back in the time machine, I was given a command by my supervisor at the time in 2002 to characterize these little objects on the sun. Now that image on the left is a image of the extreme ultraviolet solar corona. So the plasma that's radiating there is at about 1.5 million Kelvin. It's fairly hot. And you can see, like any middle-aged or any teenager, that sun is pockmarked with little spots. So there's no sunspots present, but there are lots of these little blemishes. And because you'll recall that we solar physicists are extremely detail focused, they're called UV bright points because they're in the UV and they're bright and they're points. Okay, so just remember that. Back in 2002, I wrote an algorithm to identify them in the data. My boss at the time said, well, maybe if you identify and track these things over time, you might learn something. So the question to Joe, who's just retired, Joe Gurman, is what did Joe know? I should make t-shirts up. Because clearly he knew something. And actually about 12 years later, when I come back to analyzing this data that I had been accruing daily since 2002, several wild questions started throwing themselves up. So anyway, Some of the things we noticed. So in 2012, we came back to this, and this was from an email that I sent to then the person that was actually in my position at NCAR, Maura Hagen, who's a pretty renowned upper atmospheric scientist. She was also deputy director of NCAR at the time, and was having lots of conversations with the National Science Foundation about discoveries that NCAR was making. So I showed her this, and this is literally the synopsis of a eureka moment, right? Basically bathtub, literally bathtub, eureka moment. And so if you focus your eyes on the plot at the bottom left, this is the progression of these extreme ultraviolet bright points as a function of time. I dug this is from an old email. And there's a lot going on in here that I won't explain, but the first thing we noticed, two things we noticed, was that if you focus your eyes between 2008 and 2012, there's significant overlap in these bands of things, right? So these small objects are a few 100,000 kilometers across, right? Which in the sun is small, but not when it comes to Earth. And if you catalog them as a function of time, what we noticed at the time where the sun was making no sunspots, there was at least 4 to 6 years of overlap between the bands at mid-latitude and the bands at the equator. And we thought that was really, really curious. And now the slide just got absolutely wild, right? Because there's a whole bunch of other things that we noticed at the same time. It seemed like the bands at the equator had a real end. If I skip back and now tell you to focus on this gray line in 2011, you see that basically there's stuff there, and all of a sudden, nothing. Okay, it goes. And at the same time as the stuff goes at the equator, rampant growth occurs at mid-latitudes. Okay, so basically the magnetic machine of the sun basically goes into overdrive. Okay. One of the kind of fantastical things, and we'll maybe come back to this later, is that the sun has, at least over the last 20 plus years, been extremely asymmetric. So the two hemispheres of the sun have been really kind of, I wouldn't say completely out of phase, but very not in sync. And actually, it's the asynchronous nature of it that allowed us to identify these odd start times. The other primary thing we noticed here was that the progression towards the equator was roughly linear. So at the time I had a 5-year-old, and my challenge to the 5-year-olds, can you draw a straight line through that? And she did pretty well. In fact, I allowed her to continue drawing straight lines out in time, because that means you have a predictive capability, right? So anyway, the thing that we noticed was that at solar maximum, these bands of magnetic activity start at about 55 degrees latitude. Now, if you're scholars of the ancient lore of sunspots, we know that sunspots don't appear at 55 degrees latitude. They appear at about 30 degrees latitude. And this horribly colored middle plot shows you basically a variant of a butterfly diagram for sunspots. And we see that, lo and behold, when this termination event, as we came to call it, happens at the equator, it's exactly when the sunspots switch on at mid-latitudes. And so we instantly, literally in the bathtub, put this together, started to play games with my mind. And we were instantly starting to think about forecasting. And we looked at lots of data, and I had shingles twice in the space of 18 months from looking at somewhere approaching 40 terabytes of data, going back some 70 or 80 years. Not just using data from space, of course, but also from ground-based observatories. We noticed that there was further patterns in the data. So not only could the bands track linearly, we also noticed that solar maxima in each hemisphere, so the ones that have the same magnetic polarity, are almost exactly 21.8 years apart, irrespective of asymmetry, right? So there's there's a definite cyclic behavior that's happening at high latitudes on the sun. And that allowed us to say, okay, well, if solar max of cycle 23 happened in this year, solar max of cycle 24 is going to happen, well, in the northern hemisphere in about 2012 and in the southern hemisphere about 2014. And then those bands are going to start from there and migrate at about 3 degrees per year until they reach the equator, right? So basically, this is a forecast of what cycle 24 is going to be like. And it's going to lead to the appearance of cycle 25. So if you look at these ovals, you see the description here. And I'm not playing games with you. This is from an email of September 2012. That we start to see the first cycle 25 sunspots probably in the last quarter of 2019 and going into 2020. Okay, so very optimistic crystal ball gazing, right? In the words of my homeland, fucking crazy. Was the excuse my French, but that was the reception of this. I'm going to fast forward now. 2017, you see that exactly those bands are tracking, right? So I jump exactly the same diagnostics now over time. We see the bands, and even then in 2017, you can actually start to see the UV breakpoint bands starting to appear at mid latitudes. And so there's a weird combination of diagnostics here that I'm not going to get into, but basically the one on the top is a measure of the magnetic field itself. And then the one in the bottom of these extreme ultraviolet breakpoints. And what we found is that the combination of both of those gave you all the tracks. So anyway, so I would say that was pretty successful for a wild ass guess, or a WAG. In fact, this would be a SWAG, a scientific wild ass guess. Tracking the linear behavior. So we go on. What we began to notice right about the same time in 2014 was that when we start to look at the butterfly diagram and we start to look around, we actually identified that this work had largely been done before, which is always the same in our field. Someone's always beating you to the punch. And we found a series of papers in the mid-80s from some very detail-focused solar physicists. And they called that these bands belong to a thing they called the extended solar cycle. The extended solar cycle went all the way up to about 55 degrees latitude, took about 19 to 20 years to migrate from there towards the equator. And it was tied to the sun's 22-year magnetic polarity cycle, which is the fundamental mode of the star. So a lot of this is different from the first time I showed you guys stuff. But here you go, is our graphic depiction of the Hale cycle. So now we're representing magnetic polarities as red and blue for positive and negative. We're showing the positions of sunspots, and we're showing positions of these things that we call solar filaments. So you can see that this movie itself is actually pretty old. But we actually did not too bad at pointing out the key landmarks of cycle 24. Although it was never trumpeted in the field because they still think we're effing crazy. So here's something I put together for an article that's about to appear in one of your trade magazines. We wrote something about solar cycle 25. I can't remember which magazine it's going to go into, but I can send Paul a note with a link when it comes out. But this is basically an infographic where there's about 8,000 words worth of stuff going on. Whether it's one, in the rising phase of cycles, there's 2 bands per hemisphere. In the declining phase of cycles, there's 4 bands per hemisphere, not per hemisphere, in the sun. And the whole premise here is that these magnetic bands are interacting with one another to produce the pattern that we see as the sunspots. So you guys deal with propagation and interference patterns. So basically what we're saying is the sunspot cycle is an interference pattern created by the underlying magnetic polarity cycle. That's it, simples, right? That's it. We're not saying anything more erudite than that. the big clue to us was this whole concept of sunspot minimum, right? So if you look at this infographic and focus yourself on the middle of the plot again, the sun makes no sunspots, or very few between 2007 and 2011. There are 4 activity bands between plus 30 and minus 30 degrees. There's no shortage of magnetic material there to make spots. The thing that's happened is they're all cancelling each other out. Okay, that's what magnetic fields love to do, according to my famous countryman who decided to write them down, right? Maxwell. And so what happened there is once you terminate the ones at the equator, then there's unbridled growth at mid-latitudes. And so you get this crazy interference pattern going that then shapes the sunspots, okay? We'll get into sunspot cycle amplitude in a little bit. But now I'm going to draw your attention to these kind of signature events, these termination things. We came back to these a little bit later, and this is what the termination event looked like in 2011. So this is a daily sample of data. You can see it starts sometime in the middle of April 2010, because this spacecraft was only launched in February, and it was a great privilege to go to the launch. That's something special. But you'll see what happens is the density of these small magnetic features basically goes to 0 in a heartbeat. Okay, and a heartbeat for the sun is a couple of rotations, right? You think of an object the size of the sun, basically flipping a switch on the timescale of a few rotations is mind-blowing. There's very few things that my peers will tell you happen on the sun in that timescale. Okay, certainly not evolutionary things. And so again, effing crazy is the watchword. Okay, so the big challenge for us was that the cycle 23 terminator happened. Actually, we have it down to a day. So it was February 11th, 2011. The one in 1997 is a wee bit murkier because the data wasn't quite as crisp. So 2 different spacecraft. And the big challenge to us now, as you can remember, was when will the next one occur? In 2011, we had a very fortunate circumstance where we could see all of the sun all of the time, just for 4 years, but we could actually map out the whole sun. And you know what we discovered was that this termination event was also a longitudinal problem. So basically, it's an event that starts at one localized longitude and then propagates around the sun in the timescale of a couple of rotations, which, like I said, is mind-blowing. Okay, this is just to illustrate this. Just log this one for future reference. So here's the hypothesis, right? Hale magnetic cycles overlap and interact. They have regular starts at high latitudes, which is completely contrary to theory. The migration time to the equator is pretty, it's not very variable, but it's not too bad. It's linear. The interaction between the magnetic systems is not always the same. Therefore, the sunspot cycles it produces are not always the same. The interaction between the 2 or the 4 bands shapes the evolution of sunspot cycles, including their amplitude. And you know, if you've ever noticed with a sunspot cycle, they rise very linearly, but they fall off like an exponential. So that gives you a hint that there's more than one thing going on at any one moment in time. Now, you will also maybe remember from my first talk that this is crazyville, right? And our peers were very skeptical that only 14 terminators, that's not good enough. You need to go back through the entire observational record and show us all 24 of them, or we won't believe you. So we devised a Hilbert transform technique, which identifies the maximum rate of change of the sunspot data set. And that's basically, it's what Hilbert transforms are used for in EKGs and things like that, for detecting arrhythmias and things. So not going to go into this plot in a ton of detail. Some of you may remember it, but the upper plot is the monthly sunspot number going back to 1747. That's the black dots. The red dots, and this is for Peter, if Peter's on, are the 13-month smooth variant of that data set. The blue curve is the trend that's taken from a 40-year moving window through the data. Okay. We detrend the data and then we apply a Hilbert transform to it. And the two things you notice is that it's spiky. So yeah, so a Hilbert transform is not like a Fourier transform. Fourier transform assumes that the phase of the signal remains constant. That's not true for sunspots, and so you have to use something like a Hilbert transform where the phase is also variable. And so one of the beautiful things we noticed when we started looking at the phase function of a Hilbert transform was that it, in this case, it can go through a phase of 0 at these termination points, or you can set it to be the place where it goes from plus pi to minus pi. So it does a complete rotation. It doesn't matter, it's kind of arbitrary where you set 0 or this phase flip, but it happens every single time. Okay. So our hunch back in 2014 was that this interference pattern sets the amplitude of the next cycle. Okay, so depending on the arrangement of these Hale cycle bands dictates the shape and the amplitude of the sunspot cycle. So with these 24 data points, we're going to do a little experiment, right? I'm going to look at experiment 1, which is the intermediate. So I'm going to look at these two terminators and their separation time, because I'm going to use separation time as a marker of their overlap or interference. And I'm going to compare it to 1 to the intermediate strength and 2 to the upcoming cycle. Because what I'm going to say is, right, if I draw your attention to cycle 24's bands, if cycle 23 shifts to the left, right, so if the termination point moves from 2011 to 2009, cycles are different. So it's all some growth time, decline. Well, we're going to the upcoming cycles, right? So if I look at experiment 1 and I compare the intermediate cycle strength for those 24 events, I have 0 predictability. Okay, there's no relationship. Everything fits equally within that data set. But that's not the case for the upcoming cycle strength. So at some level, our hunch is correct. But we're now going to highlight the issue, okay? And just for fun, just for shits and giggles, right? There's a magenta point on this. And this is actually the week that this work was done. A group of my peers were meeting in my building to talk about what solar cycle 25 was going to look like. Okay. So this was there was a sunspot cycle prediction panel was conducted. And my erudite colleagues decided that sunspot cycle 25 was going to look a wee bit weaker than cycle 24, with a peak amplitude of about 115 spots in the middle of 2025. Okay. Now, when we did an initial guess of when the terminator was going to happen, we thought it was going to be about a quarter of years. We're not going to get into that. We can talk about that later if you want. But that's basically the vulnerability of using Hilbert transforms to predict the future. Boy, have we learned a lot from that. Anyway, but the initial guess would then put solar cycle 25 slap bang about 225 to 240 spots, which would made it in the top 5 of all time. Okay, so it's huge cycle. You'll notice also that this relationship would also have predicted cycle 24 bang on the nose. Okay, and nobody got cycle 24 right. Anyway, so this is another thing to think about. So we can observe the Hale cycles. Data seems to support this concept that these Hale cycles interact in such a way to make spots and make sunspot cycles. I'm giving away the game in the fourth bullet point. We now have a finalized prediction for cycle 25 because our friend the Terminator arrived last December. I'm going to show you the signature of that in the next slide. But that means that the Sunspot cycle has come down to about at least 190. And that puts it above the historical average. But the problem is that our method underpredicts big cycles. So there's still the potential for this to be double the size of cycle 24. So now we're getting into the cheese factor 50, okay? If you notice carefully, the Terminator in the middle has two different sun images for eyes. One from September 1997 and the other from February 2011. Nobody's actually noticed that, although we've been using this graphic for a long time, but they just thought it was the beady eyes. So the Terminator arrived on the 13th of December last year. So for the first time, we've observed the death of a hail cycle in real time, which is kind of cool, I guess, although maybe I'm the only person remotely excited about that. You have been seeing a growth in sunspot numbers since then, and also a growth in F10.7, so your solar radial flux, which is ionizing the ionosphere and giving you good propagation. But, and this is the big but, it's not really gone out a second year yet, which is kind of baffling. But this is the problem when you observe stuff in real time. So I'm going to show you a little bit of why we think that's the case. Okay, sorry. So here's the Terminator event itself. You probably know we've been watching this very diligently for a long time. And it was getting a little bit depressing because on election day 2020, it looked like it had hit. And we were all excited. And then it didn't. And then again, in the middle of 2021, it looked like it hit again, and then it didn't. So you can see the little burst of activity starting in November of 2021 in the Southern Hemisphere. And then we had this other faint ghost in the middle of 2021. But really, really honest to goodness, it happened on the 13th of December, 2021. So I'll show you more details about this. So here's another schematic with some more bright points in our image here, laying out different arrows showing the 2011 Terminator, Sunspot cycle 24 bands, the 25 bands that we've been observing for now since 2016, and the 2011 Terminator. So you can see its characteristics are all pretty much the same. If I put it in a somewhat broader context, again, there's all those key features that I showed you earlier, and the drop in activity at the equator again. I'm coming back to it just to show. So it's funny. Remember I talked about longitude earlier being an issue? Well, this is a daily plot. So you imagine the sun. Oh, don't even put my camera on so you can't see me gesticulating. But this is a daily plot. So the sun rotates about 8 degrees an hour. And so you can see that, sorry, it's 8 degrees. Oh, hold on. Ah, there we go. So it's spinning around. So the central meridian of the sun traces out here. And so what you're basically seeing over a month, you're seeing a rotation. Okay. So what you're basically seeing when you get that dark green line that's vertical, it means that there's a set of longitudes on the sun that aren't behaving themselves. Okay. Right? They're bastards, for the lack of a better term. And so we've been taking these diagnostics for a long time too. And so this is what happens when you slice through the data set at different longitudes, across different times through latitude. And so you can see the bumps created by the activity bands. And the idea here was just to compare what the present situation was compared to the situation in 2011, right? And so the plot on the left-hand side here is what's going on right now. And so it's basically flat as a pancake at the equator, which means that cycle 24 has absolutely left the building. Okay, kind of. I'm going to show why in a minute. So now we'll go back to my longitude plots. So on the left side is the southern hemisphere. So this is at about 30 degrees latitude. So you're looking at slap bang in the activity band, and you can see these dark blotches are basically active regions popping up. You can see between 2017 and 2021, there's nothing there. Then all of a sudden, boom, switches on. You can see the election day burst, and you can see the mid-21 burst, but now it's hitting a lot of different longitudes. The same in the northern hemisphere. And then if you look at the equatorial version of that and in the middle, you can see the drop of breakpoint density in May of 2021, which then started propagating eastward, but then died. It fizzled out. Okay. But then it happened again, shifted about 60 degrees to the right, and it's pretty much complete now. Almost. Okay. This is the whole point about second gear, right? So it's gone through first gear, it's gone through second gear, it's having trouble getting in the third gear. And why? So when this thing hits and is complete, what you're basically seeing are tiny, tiny residual magnetic fields of the last hill cycle floating around. They're decaying, but they're not decaying very quickly. And so when this thing is complete, this entire band at the top will be red. Okay, so there's residual magnetic field floating around that's stopping it from going into the next gear. This is a bit of a confusing plot, like most of the plots I've showed you already, but this is the one that's relevant to you guys. We know for a fact, because we've analyzed the data over the last almost 100 years. So actually the data for the radial flux goes back to 1947. So 80 years, 90 years, wow. Once the average radial flux goes above 90, the terminators happened. And lo and behold, it crossed that path in the middle of December. It hasn't come back, and it won't come back again until 2026. So this is the ramp. So clearly, the solar radial flux is showing the same behavior. Here's another look at the solar radial flux now, comparing it also to evolution in real time. So remember I said that there's been different stages of evolution. So up to the middle of in the middle of 21, it looked like it was going again. And so you see this drop at the equator. So what actually happened, the solar radial flux basically jumped up 5 units. So you can see the rotational minima just boop, just jumps up. And then when you get past December or the middle of December, it just starts ramping up. Right? So that's a growth phase. For those of you other nerds, so if there's some high energy particle nerds out there, here's what the cosmic rays do. Right? So it's the same thing, but in reverse. Right? So the sun's magnetic field protects our planet from cosmic rays. So as the sun's magnetic field expands, the amount of cosmic rays actually get deflected and don't penetrate the Earth's atmosphere. So it's the same thing in reverse. Okay. So these are all indicators that our star is definitely transitioning into this next state. Here's a plot that I made, which I'm going to rub my colleagues' face in. Okay. Because I'm not like that. I'm not competitive in the slightest. Okay. But if you want to look at this carefully, so this is the number of sunspots in a given hemisphere of the sun. So red is the north, blue is the south, white is the total. Do you notice how bumpy it is? How spiky it is? Now compare when the spikes occur to when the bald patches occur at the equator. Just visually. Pretty good, huh? So in other words, when the bald patches are happening at the equator, there's actually activity being spawned at mid-latitude, so 30 degrees away. So in other words, this idea of how these bands in magnetic systems talk to one another is exactly being exemplified in the data. on a real-time basis, right? So these old models where these big magnetic systems cannot talk to each other are crap. Okay, that's a scientific term to characterize that. Okay, total crap. Here's the radial flux. See the same thing, bald patches, spikes, and then once you get past December of 2011, you get the ramp. And so you can see the rotational minima just kind of stepping up and up, and it'll keep stepping up and up, probably for the next 2 years. Okay, so here's the question that my kids ask in the car all the time: are we there yet? And my answer is, I'm really disappointed to say maybe actually not. Okay, so yes, the Terminator has happened, but it's still going. So it's taken now, we're in March, so we're in our 4th rotation, 4th month. And it looks like there's residual cycle 24 activity in the northern hemisphere, a few degrees above the equator. And I think that that's what's stopping it from really cranking up another couple of notches. For those of you that study the sunspots and look at the Belgian website, I don't have the website address on here, but I can certainly furnish it. This is the updated data on a day-to-day basis, and you can see the effect that the bad longitudes have on the data. Okay, so it actually ends up pulling the average down. So you see, this is the sunspot trace in green, this last rotation. Red is the current one. You can see that these basically are, it's the same longitude that's pretty much, it's not dead, but it's not exactly alive either. So we need that to go away because it's quenching everything. So like I said earlier, we revisited, so we've now used this December 2011 Terminator to look at, you know, what does it mean for our prediction of cycle 25, okay? So again, it's about double cycle 24. You recall a lot of the press talking about how it's going to be smaller, equal to or smaller than 24. We still think that's a load of guff, right? That's another Scottish term. So you're learning something at least tonight, some Scottish vernacular. It's going to be around just a wee bit bigger than average, which is actually still pretty good, which means it's cycle 23 level, okay? Just to put it in a bit of context for you. Maybe a bit higher because, well, we're not sure that we don't have that many big cycles. So still pretty confident. How's it progressing? Here's a plot we made also for the ham radio journal that shows our forecast in context with where the data is right now. I think it's doing pretty damn well. This is with the adjusted forecast, so you can see that the red thing here is about cycle 24 kind of magnitude. It could be higher than that. I think we're being quite conservative. If you want to look at it on a day-to-day basis, you can point yourself at this website and you can cheer along with us as the black data points get updated every month. The green data on this are the daily sunspot numbers. The red are the unverified numbers. So it's basically the Belgians come along at the end of the month, verify the data for the last month, and then create a new monthly average so that this is current through February. The March numbers will be put together in a couple of weeks, and we're probably going to be sitting about 70, 75 kind of level. Okay, so it's going to take a little jump, but not a considerable jump because of this longitudinal problem. Okay. And for you guys, we've actually been working on this for quite a while. We have a self-consistent forecast tool. Again, very conservative. This is now the daily and monthly F10.7 tracking against what we forecast to happen. So we're going to look at a solar flux of, I think, somewhere between 180 to 200 at peak. That peak's going to be middle of 2024, probably. So you've got another couple of years of growth before it goes into decline. We anticipate the next Terminator, but take that with a huge pinch of salt, to be sometime in the middle of 2032. Okay. Just that's based on historical evolution and my 5-year-old drawing straight lines. So believe that as much as you want, okay? But she's actually been very good up to now. So I know I went super fast. I'm my own worst critic. I think we've done as good as we can do. I really wish this was cycle 19. Really do, because it would really shut people up. The big thing for us is this contrast. So from a physicist standpoint, and this is something I've got to really emphasize, is that producing a cycle that's almost twice the amplitude of the consensus prediction in the community points to a real issue, right? So if our crazy forecast is right, that also means that all the other crazy crap I've been telling you about tonight about hail cycles and interactions and all these other things that look like they're quite plausible based on the data are also probably correct. Well, just for you and I and anyone that's watching on the stream, that means that there's about 75 years worth of research that needs to be revised just a little bit. Okay, maybe considerably. And I won't drop expletives there. I really would love to, but. And so I'll leave that. I think this is the last slide. There's that horrible green plot in context. Remember, it's conservative. I think it's going to be lower. I think we're going to be looking at something that's kind of akin to cycle 23. So it's not going to be quite as exciting as we originally thought, because this damn thing is complicated, right? So we're learning as we go. You guys I've been really happy to observe this with you guys in real time, and it's a huge credit to Paul for picking me up and giving us some real exposure. It's really brilliant. So, and with that, I think I'm going to leave that up like this, and I'll open for questions if there are any.
Thanks, Scott. That was wonderful and encouraging for those of us that want more sunspot cycles. So probably everyone's pretty much muted. So if you have any questions, make sure you unmute before you go ahead.
I have a question here, Scott. Your prediction shows a double hump for this cycle.
Yeah.
Why are you suggesting that it's going to be sort of a mirror image of 23 then with the double hump, and 22 as well, I think?
Well, remember how I said most of the time the sun's asymmetric?
Yeah.
Right. It's very rarely symmetric. Okay, very rarely. Even though the old theorists would love to say that it's symmetric, it's really not. And hardly ever. And so the double hump cycles are all to do with hemispheric asymmetry.
Okay.
And so if you look at the cycle, actually cycle 19 is a bit of a freak, because it's one of those times where the two hemispheres are on top of one another. So you can imagine if they're slightly offset, you get this weird thing. But if they synchronize up, you get this amplification factor,
you get that,
right? So
high peak. Okay.
Yeah. So that's the reason. And that green curve, Dana, is built off of a historical average.
Okay.
Right. So we've basically used, there's an old meteorological technique called a superposed epoch analysis. And so what we've discovered is if we use the terminators to define basically like a sun's year, we can actually develop very robust climatology of what the sun's going to do over that 11-ish year period. It's really good. So we're pretty confident that
Okay.
it's going to look like this. So
Got a question, K1HTV, Rich.
go ahead, Rich.
Scott, you had shown a possible double hump. Can you show that slide again and indicate the months that you predict that double hump will occur? The reason I mentioned that, back in cycle 23, the propagation of F2 with that, when the high solar flux occurs, it really has to be placed at a certain time part of the year in order for us to really get a good propagation. In the case of 2023, in case of cycle 23 in the year 2000, in December, we had an opening, a 6-meter opening to Europe. Again, continues until January, but by February, it's gone. And that's not unusual to, it start late in the year, goes through the December, January, sometimes into February, then gone. So if the peak occurs and the double hop occurs where the hop is not in those months, I think the chance of F2 skip on 50 megahertz is going to be pretty slim.
All right, well, let me do something on the fly here. Hold on, let me look. Because there are indicators. Where do I have that? I do have, we've been working on the double hump nature. So just bear with me just a second while I pull something else up. All right, so you're gonna have to destroy all the video of this, okay? Destroy all the video. I'm gonna switch from one share to the second share.